Hi, I'm Mars Berry. My day job is training the next generation of outstanding teachers at the University of Roehampton, which I enjoy very, very much. Roehampton let me out from time to time to go and do other interesting things, such as being with you here today. I was part of the drafting panel who put together the English computing curriculum, so if you are following that, blame me or thank me, depending on how that's going with your guys. Before the whole Roehampton gig kicked off, I did 18 years across 4 different schools, all of which was in the independent sector as it happened. So much of that time as an ICT coordinator, 3 years as a primary school head teacher, which was hence prematurely grey hair. They're not quite as old as I look, although rapidly approaching that point. When we think about the computing curriculum, it's so easy to just focus on the coding bits or the computing bit, or the computer science bits of it. And when we drafted it, we very clearly had in mind it wasn't just computer science. There are 3 clear elements to it: computer science, information technology, and digital literacy. If you want to think of them in those terms, think of them as the foundations, the applications, the implications of the subject of the discipline. Much of what I'm going to say today is focused on the computer science bits, particularly the programming bits of the curriculum, but I think you need to make some mental adjustments in your head and say, yes, that also makes sense in terms of the IT bits, the getting useful stuff done on computers, and that also links into that implication stuff of thinking about the impact of this technology on us as individuals, on us as a society. The whole thing in one slide. What we're going to do over the next, 50 minutes or so, is walk through this list of, I'm afraid, 10 bullet points. My usual way of doing this thing is to spend most of the time on the first 3 bullet points and then have to dash through the last 7. Somebody waved about halfway through and say, Mars, move on, please, move on. So yeah, that's pretty much the list that we're going to work through. I'll put that back on at the end, and then we'll do that actually didn't seem that important. Or, Mars, why on earth didn't you say? So be thinking critically as we're going through this list about, is this actually an important approach to teaching computing? And surely there also ought to be that. What I'm going to do is talk a little about what our experience has been 1 year in terms of the strategies which we seem to find working when it comes to computing education. Nobody's written, well, some people are writing books on this, but nobody's got the definitive text on this is the way to teach computing. It's not like maths education, it's not like science education. We are making it up as we go along, which is tremendously exciting. It really is. That we are creating this new body, not of subject knowledge, that's pretty much written by computer scientists, but of subject pedagogy. We're figuring out for ourselves the approaches which work in our schools, in our context, with our learners. I think we can start to see some patterns emerging, some common ground around, well, actually most of us who are doing this sort of thing think around this list. I've tried the list out with other good and noble people in the domain, and yes, there are things around which I might put more emphasis than they might put emphasis, but broadly speaking, a lot of us who've been involved in this process agree about most of the things on that list. That isn't the same as me saying, yes, this definitely works, but it does seem to be a summary of where we are a year in. Does that sound okay for you? Okay, let's get on with the show then. So, I've actually moved the order round when it came to the deck, but not at the introductory slide. So rather than going through the list in order, I wanted to put this one first, because it isn't about the coding. The new programme of study says what we're aiming to do here is develop computational thinking and creativity. It doesn't actually talk about coding at all. It does talk about programming. But this is much more about tools to think with, about thinking, about learning, about learning. As Seymour Papert had right, way back in 1980 when we were doing the logo programming the first time round, it wasn't that children needed to learn how to draw triangles using turtle graphics commands, using logo commands. It was much more about the children who learned how to program a computer could start thinking about, having concrete models to think about, thinking to learn about learning, and thus develop as psychologists and epistemologists, as philosophers, if you wish. Roy P., who came after Papert's, on the back of Papert's work and did the randomised control trial studies, checked where the Papert was right, because Papert tells just lovely stories but doesn't actually give us any evidence that all of that actually works. So Roy P. went and got some of the evidence back then, and he gave the control group thing. So half of you learn how to program in Logo, half of you just have normal maths lessons, and then we'll have a look at your planning skills at the end of that process. And Roy P. found that actually the Logo programming hadn't in and of itself developed these planning skills. It was teaching that was where the benefits came. So yes, everybody learned how to program in Logo. This wasn't beyond the elementary school children with whom he was working. But they didn't get further into Logo. They never learnt about recursion or variables or some of the more complex constructs of the language, unless that was something that got taught. And Roy P. said they didn't learn about how to apply this more generally, what we now call computational thinking, unless that too was something which was explicitly taught. Here's the phrase which we start with, which I've already hinted at. That's what we're aiming to do here. Understand the world, change the world. That's our success criteria, in terms of Ewan's objectives. Have your pupils understood the world? Have they changed the world? Tick in both boxes and job done. Let's go on, move on to something else now. So we talk about computational thinking. I think Jeanette Wing coined the term, although Papert wrote about it earlier. In fact, she talks about it as taking an approach to solving problems, designing systems, understanding human behaviour that draws on the concepts fundamental to computing. It's looking at a problem, looking at a system in such a way that a computer can help us solve those. So what are those concepts? I think top of the list for me is logical reasoning. Do you not want your pupils to be reasoning logically? Wouldn't it be a really good idea if they could spot flaws in logical arguments, if they could give reasons for why something works? Programming is a great way to develop that set of logical thinking skills, because when you're working with a computer, you can make confident predictions about what will happen. Give it the same program, give it the same input, it will produce the same output, unless you're running Windows 8, of course. Okay, we have in computing this notion of the algorithm, of the way of solving a problem, the way of getting something done. Again, you do that in programming, but you want your pupils, I'm sure, to do that across the curriculum, to think about how to get this particular thing done, to think about an efficient way of doing these things. So what do we mean by an algorithm? We mean a sequence of steps, a set of rules in order to get something done. This one is represented as a flowchart, and it's worth getting children to think about how they're solving the problem before they write any lines of code. The one on the board there, does that look at all familiar to you? When might you use an algorithm like that? This is not a rhetorical question. Well, it's not purely a rhetorical question. Anyone? Yeah, lessons. We do this sort of thing, don't we? Your mental arithmetic warm-up, your spelling test, your whatever. You ask a question, the child responds, and you tell them whether they've got it right or not. It's what we do. Most educational software follows that algorithm. A computer scientist looking at a problem, looking at a system, will break it down into its smaller parts. When you're teaching your children how to write stories or do a research report, you get them to break it down into the smaller bits and deal with each of those separately. You have to do it in programming, but you do it across the curriculum as well. We look for the patterns, we look for the general class of problems rather than solving the individual problems. We also look at how other people have done these things. A good computer scientist is a lazy computer scientist, looking for the easier way to do things, looking at the way other people have solved the problem and borrowing from their ideas and generalizing those results. And for Jeanette Wing, the key element of computational thinking is this notion of abstraction, of managing complexity, of having black boxes inside which we don't worry too much about the detail unless we need to. Curriculum design is like that. A Secretary of State may say children should learn to code. Other people then put that in terms of particular objectives or bullet points on a program of study. Other people produce schemes of work. Other people implement those as lesson plans. The Secretary of State is not interested in your lesson plans. Your school principal is probably not interested in your lesson plans, yeah? But it's important to have that detail at the appropriate level. And again, with computing, you've got all of that going on. We don't worry about what happens inside the machine on the hard disk inside the memory chips, but we trust other people to have done that job. Okay, so that was my first point about computational thinking rather than coding, and all the time keep coming back to those ideas. Second point, it's easier to read code than to write code. So in Key Stage 1 of our curriculum, we have use logical reasoning to predict the behaviour of simple programs. Yes, you should be able to do that on the machine, but my hope would be that the child could look at the Bebot instruction list and predict where the Bebot will end up, not merely by typing in the instructions and pressing the green go button, but by reading the code and saying, it will end there, Miss whichever. And similarly up in Key Stage 2, to be able to look at some code and say why it won't work. Yes, you can do that by testing the software, by typing it in and seeing what happens. But the higher order skill is to be able to reason logically about that. And we have, data from, or research based on undergraduates learning computer science, which confirms this view, that it's hard for them to start from a blank screen and to write some code in a language which they've never met before. Your pupils might find the same thing going on with Scratch, but it's much easier for them to reason about code. Show them a program, ask them what it does. So here we go. Show them a program, ask them what it does. Any thoughts? Very good. Oh, it's what do you think it's going to do?
It's going to give us a kind of flower made up of squares, isn't it?
How did you get there so quickly? Just you've clicked on the deck, haven't you? You followed the links. Okay, explain to us how you know that.
We've got
Unless it was a really lucky guess.
We've got a nested thing there. In the middle, you've got a repeat for bit.
So you recognise the pattern here. This is going to draw a square, isn't it? Yeah. Trundle forward, 100 steps, turn right through 90 degrees. Yeah. 4 of those make a square. We can explain why if we go into the abstraction about, well, that's the property of a square. So we've got a square going on.
Yeah.
And then,
but you're repeating that square 10 times, and then twisting the square around 36 degrees. Yeah. Which 10 lots of that would make 360.
And that's where the magical numbers came from there. So yeah, anybody know what programming language this is?
Is that Logo?
It is Logo, absolutely. This is a language, what is this, 45 years old, pretty much now. And those of you who never programmed in Logo should still, I hope, have some feel for what this is going to do. Is there anybody in the room who wants to actually have this proven to them, who'd like to see it working? Yeah. Or is the expert, okay, you want to see some code? Okay, so there's an online logo interpreter, which is really very, very nice. So if I take my code there, I should just be able to copy them. Got to exit the presentation. Okay, so I just copy my code here. My mouse isn't working very reliably. And paste that into the box at the bottom of the screen there, run the code, and ta-da, we get our square rotated for 10 times round each through an angle of 36 degrees. The proof of the algorithm is in the running it, but actually it's the thinking about it, the being able to say what it does, that I think is the important thing. This is a famous problem. Okay, given to first-year undergraduate computer science students. Okay, again, who cares what the programming language is, but have a look at the code. Int A is 10, int B is 20, A equals B. Could you please write down on a piece of paper what will be the values of A and B when you run that program? If you don't have a piece of paper, then pad screen will do. I want to do the thing about there are no wrong answers, but actually there are wrong answers. Okay, nobody's writing anything down. You're all very good at that. All doing it in your head. Okay. Do I have somebody willing to volunteer and say, I think it is?
I'm not sure, but I think it might be they're both 20.
You think they're both 20?
I don't know.
Okay, we'll come back to that. Anybody want to go for a different answer? I mean, what we're getting to is your mental model of how variables work on computers. Yeah? And you're absolutely right, both of them are 20. We take the number 10 and put it in memory location labeled A. We put the number 20 in memory location labeled B. And then the next bit, which is the tricky bit here, A equals B, is generally understood in most languages as look in memory location B and copy that value and store it in memory location A. So in most programming languages, you will get the numbers 20 and 20 in the two variables. Okay. The really worrying thing, okay, don't worry about this, but what Donardi and Bornak found is that they set this question right at the start of the course, and those who got it right went on to do really well, and those who got it wrong didn't do very well. Even, so their argument is kind of, well, it doesn't really matter what you do in terms of teaching. Some people get it, some people won't. If you get it, that's fine, you can do whatever. I don't think that works in our context because we've got to teach computing to everybody. I've got another one here. Again, have a look at this, see if you can figure out what it's doing. Talk to one another. Reason about it. Reason logically. Very good.
What is
Okay, has anybody got their view of what this is going to do? No? Okay, don't worry, it's fine. Really don't worry. Go on.
Times tables.
So again, it's times tables?
Yeah. It's just basically saying times between 1 and 2, isn't it? I don't know.
What is it? When I run the code, what will it do? Can you explain?
I don't know.
Something about times tables, which is great. Okay. Anybody want to go further than it's about times tables?
I don't understand. I know that what I don't understand is a bit the answer is A times B star bit.
star is a time sign?
Yeah, which I thought. Yeah.
What about feedback?
I've got it now.
Okay, go on then.
So you're coming up with two random numbers between 1 and 12.
Okay.
You're then asking what's that number times that number. Then they're putting in an answer, and if their answer is that number times that number, you say well done. Otherwise, you say no.
Yep.
It's a times table test.
It's
Yeah.
times table test. It's pretty much the algorithm that I showed you as the flowchart
Yeah.
earlier, isn't it? I'm going to keep asking some questions. I'm going to tell you whether you get it right or wrong. Had you ever programmed in Python before?
No.
Okay. Now that is impressive. To have looked at a collection of, 10 lines of non-trivial, it's not hello world here, Python code, and been able to figure out what this program does. And that's the reasoning logic, the reading it before you write it. Go on.
I'm confused by the second string for I in range of
Fine, okay, but I mean that's great. That you're thinking about what does that mean? Anybody like to have a go at what's going on there? What is this 4i in range 10 likely to be about?
That's the first number, is it?
No. Go on.
Is that about using the number system we're used to with a base?
Oh, I love the idea that I have to tell Python to work in normal numbers. Alas, no. Wouldn't it be nice though if it was? That's so
Is it kind of a
cool.
loop?
It's a loop, yeah. How many questions is it going to ask?
Oh, it's asking 10 questions.
10 questions, yeah. Do we not always just do 10 questions?
Yeah, but I don't see where the I comes in.
Okay,
Just looping.
in Python, just in Scratch, you would just say repeat 10.
Right.
Okay,
Yeah.
and with a group of pupils, obviously you wouldn't go straight to Python here. But here is a Scratch program. What will this do? Here is a Logo program. What will this do? If once they give you that code, Simon, what do you have to change there? If your school has a policy of we only do tables up to 10 tens rather than 12 12s, 2 lines of code that you need to change to do 10 tens rather than 12 12s.
Yeah. Comma 10.
Yeah.
Comma 10.
Okay, if you wanted 8 questions in your tables test, if you wanted to make it an addition test, not a multiplication test. Yeah. So, none of you, you've never programmed in Python. I assume nobody else in the room has ever programmed Python before. But you can take some Python code and tweak it and adapt that. For me, this is the first step towards learning to write some Python code. Have a look at other people's Python code and see how you could adapt it. And you could do the same thing, obviously.
Max,
Yeah.
just one very last
Go
question.
on.
So you've decided there not to use the 0 in the times table?
Yeah, because the answer to 0 is relatively straightforward. I suppose the answer to 1 is straightforward.
My
Yeah.
kids
But,
don't believe
okay, if I wanted to do 0 to 12, then you could, I'm sure, tell me which lines are going to change that.
0,
given that I just waved my fingers in the direction. Okay, we could see the thing on screen, but I'm conscious of time passing. So I've already got to the point here, really, that it's easier to edit code than to start from, I want to say start from scratch, but if I said start from scratch, you'd assume, we're talking about cats on the screen. And this is what happens. Here you go, 6 software projects. What do all of these have in common?
Open source?
Coding.
Spot on, thank you very much. What does that mean?
It means they're available for free,
And?
and you can modify them.
Yes, absolutely. So yes, it is free in the sense of free beer that we can, we don't have to pay to use any, to download any of these things. Okay, for Android you kind of need to have a device that it runs on, but Android itself is freely available to the device manufacturers. But you also have, it's free in the sense of free speech. We can see how the code has been made, we can change that, we can modify it. Good luck if you're wanting to modify the Android operating system. But, with other things in here, Moodle and WordPress, loads of people contribute modifications, extra modules into that code base. So you have huge software projects like Android, like Scratch, like Firefox, which are developed by a community of people contributing their own suggestions for improvement. We have this sense of the 4 software freedoms: the freedom to run the program as you wish. Yes, of course, that means you don't have to buy it, but the freedom to look at how it works, the freedom to share it with your friends, and the freedom to share your modified versions. This is part and parcel of what we mean by open source software. And you get this going on not just with Scratch's code itself, but in the Scratch code base. So what have we got? For a commercial scheme of work that I wrote, we have these games. I think it's like year 2, we bring this in. So here are some games written with Scratch. They're not particularly good games, but my duck shoot one there, we can play it, but that's not the point, really. We say to the children, take this code and see if you can change it, see if you can improve on this. And there are like 137 modifications of my duck shoot game out there because children took that code and made it do different things. Some of them much more ambitious than others. But you can do that with Scratch. You can do that with a lot of this sort of thing because you've got access to the source code in there. Next slide, please. Okay, so we can take a bit of Scratch code and modify it. We can tweak it. We can change it. We could play with this one. All of the slides are online. If you want to have a go at some of the exercises, that's absolutely fine. But it's gone into French. That was unexpected. I know why that is. It's because I mucked around with the language pack earlier. So here we go, back in English. Here is my code. Now, this is a complex idea. We're getting to the notion of recursion. We have a procedure here called tree that calls itself. And so you get something which looks really quite complicated when you run the code there. There it goes. So each branch of the broccoli is made up by smaller branches of broccoli, and the turtle runs like that, which is fine. What's interesting, or one of the things which I think is fairly interesting, is changing this code and seeing what effect that has. So instead of 0.8 and 0.6, what if I made that number 0.5 and that number 0.9? Would that make any difference? What would happen if we ran that code? If instead of 15 degrees here, if we made that 20 degrees, and then 15 degrees there, what would happen when I run the code? How different would the tree look? It's quite disappointing somehow. But you have that sort of experimental approach to changing parameters. And I've, of course, only tweaked minor things there. You could have much more fun sort of tweaking things much more dramatically than I just demonstrated there. Okay, so we'll move on to our 4th one now, which kind of links to what Ewan was talking about earlier, about those stupid little exam questions and looking for the interesting context. David Brown, who's Ofsted's national lead for computing and e-safety, when he talked at the... Sorry, Ofsted quote, photobomb. Okay. When he talked at the launch of Barefoot, he put up some slides about what he thought outstanding computing teaching was. Ofsted then told him to take the slides down because they don't do that sort of advice anymore. But, he published them. They're used under the terms of the Open Government Licence. This is what he says. that it's an outstanding curriculum if the contexts are relevant to people's lives and reflect the increasing use of computing in the world of industry. That's not drawing little squares, it isn't. It's solving interesting problems. Excellent links forged with other agencies and the community to provide a range of enrichment activities to promote pupils' learning and engagement. Links with other subjects in the school are productive in strengthening pupils' learning and computing. That's so much easier for us in primary education than it is for your friends right in secondary, because often we're teaching all of the subjects on the primary curriculum and we can make those connections. Pupils are expected to use their computing knowledge, skills and understanding in realistic and challenging situations. Keep coming back to that idea of realism and challenge. There's an organisation called CBI Apps for Good, which have this year-long app design project. And it starts with you in sort of problem finding. Think of something which a mobile phone could help with. Think of the situation, the challenging, the realistic context, where a new app actually would be a really useful thing to do. Then you go about pitching the thing, you do the whole Dragon's Den type proposal thing, and then you go into the design phase, and then and only then do you actually get down and start writing the code to make the app. And not all of the pupils who take part in this actually get to that last stage of writing the code for the app, but the design bit and the finding the problems and thinking about how to solve the problems. So some of the winners last time, I love the notion of chore attack inspires work-shy kids and flatmates to do their share of the housework. Gamifying housework tasks. Looking for the perfect space for your children's party, find and rate venues in your area. I'm surprised nobody's, well, somebody has done that now. But finding the problem and coming up with, this would be a good way to solve it. Challenging realistic context. Similar organisation, Young Rewired State, their Festival of Code each year, involves young people working with software developers to solve difficult problems with public open data sets. I think the best in show this year was this pumps project, which does the number plate recognition thing and looks up the car's number plate in the big public database of what car number plates relate to, what the car is that the number plate relates to, and then checks whether the car is diesel or petrol engined. And if you pulled up to a petrol pump with a diesel engine car, it shuts off the supply of the fuel. Has anybody ever had to have their whole car tank pumped out because they... Is that not a fabulous thing? Should not all petrol stations have that?
Yes.
Solving realistic and challenging problems, yeah? And, they actually made the thing, and the thing worked. As part of I was helping with putting together a lovely BBC programme about called Cracking the Code, which took real-world computing problems, contexts, and then linked them to classroom activities. So we had the sort of classroom activity of create a simple automated driving simulator, which linked to the trip which they had, I can't see it on the slide, here we go, which linked to the context of Silverstone, where they have the real simulator. You go around the Silverstone track in a simulator, or you go around a simulation of the track in something that looks like a car and is aware of all of the physics. So real-world context then linked to some sort of vaguely relevant classroom activity. I mentioned that commercial scheme would work earlier, so switched on computing. What we did was look for real-world context in which software computers are used, and then build a unit of work around each of those things. So year twos, we are photographers. They use digital cameras at home. They'll see their parents taking photographs. Meet them there and take them on. So, not just taking the photographs, but thinking about how camera works, how the image is stored, getting good at taking good photographs, and choosing the best of those, using software to edit those. Remember, it's not just computer science that we're trying to teach here. And then you get into the whole sort of cryptography thing, and that, in this day and age, is a very, very interesting and important context. So what we can do is create our program which models very, very simple ciphers. This is using a version of Scratch called Snap. I need to step out of the full screen mode. And Snap goes a little bit further than Scratch in that it allows you to create functions. So I don't think I've got the audio working properly. Listen carefully. So we're communicating in Morse code there. Okay, we get the idea. Stop! Okay, we can set up a cipher which is a random swapping of the letters there. So letter A swaps to G, B swaps to Y, C stays as C, D swaps to E, and then we can encrypt some message like hello in that cipher text there, and it comes back as KNPPL. And then you can do the whole sort of cryptography analysis about what was the code that you used. Realistic, challenging situations. Cryptography matters. Really does. Okay, as does making things. That at its heart, this is a creative subject. And I come back to Seymour Pappert's great insights, that learning, understood by him as building knowledge structures, he worked with Piaget in his younger days, happens where the learner is, particularly when the learner is consciously engaged in constructing a public entity, making something to show to others. This isn't just a computing thing, but it is so a computing thing. Do you not find that your pupils learn more when they're writing a story to show to others, when they're putting on a play to show to other people, when they're making a painting to show to others? It's not looking at other people's paintings and saying, yes, that's a really good piece of work. It's making the painting where the learning takes place. It's writing the story, not just reading the story. The learning seems to happen particularly effectively. And of course this happens in the context of computing, which is where Papert was coming from here. Lovely as the reading the code and the reasoning about the code is, the writing the code really does seem to make a difference here. Any of you working in early years? Excellent. Do you still give your pupils things like this to play with? I'm so pleased to hear it. Why?
It challenges them, it works on their physical development.
Of course, and this matters. Yes. Somebody said play. Play is really important. We're allowed to play with computers a lot later on than other subjects get to in schools. I think, yes, you're right about the fine motor skills and the problem solving, absolutely. Typically, it's a problem that they set themselves, I would think. Please tell me you don't sort of on your desk at the front of the room build a castle and say, now children, could you make one that looks like that, please? No? That's it, okay? It's a medium for their creative expression as much as anything else, and they learn through making something, ideally to show to others, but just for their own sake, often. But they also learn about how the world works. Frobel invented this sort of block, and I think Piaget after him would say a child's understanding of the world comes through playing with toys like this, that you pick a block up and let go. What will happen, please? Thank you. Okay, there was a moment there I thought I got a room full of, about 15 primary educators and only one of them knows which direction gravity works in. Okay, that's reassuring. Thank you very much. Yeah? And you learned that through playing with things like this, I assume. Not through sitting there on the carpet in reception in kindergarten and being told, now, gravity works downwards. Children, which way does gravity work? Very good. Okay, yeah. You learn through play. The number is conserved. The number of blocks doesn't change, except with Lego, where it does seem to change randomly. The shape of the block doesn't change, even if you turn it round. That some structures are more stable than other structures. Your problem solving thing. How do I get this to stand up? That some structures are perhaps more beautiful than other structures. Understanding of the world comes through making things with blocks. And similarly, I'd argue with Scratch. Oh, yeah, the other thing. Not Frobel. Frank Lloyd Wright, great American architect, went to a Frobel kindergarten and said how that early work influenced his later development as an architect. It's plausible, isn't it?
I used that to teach computing earlier.
Yes.
Blocked.
Say more, please.
So we've got Jenga. There's Jenga.
Yay!
So basically what I've done is put colours on the edges of the blocks and numbers and letters.
Yeah.
And so now instead of just pulling out blocks, I say pull out the red block, pull out the blue block.
Yeah.
What happens? And then we get the kids to write them down. So this is like kids who are 4 or 5 years old.
Oh.
So that they're playing, but also kind of doing early coding.
Yeah.
Pseudocode.
And the link with Scratch here is not coincidental. Mitch Resnick, the man behind Scratch, his group at MIT is the Lifelong Kindergarten Group. Frobel invented the kindergarten. These are what we still play with in kindergartens. Mitch Resnick is on the board of Lego. Lego, I think, have updated versions of these from what I've seen. So that connection between the blocks of Scratch and the building blocks is not coincidental. More building block stuff. I don't have the audio plugged in, so I can show you what's going on here. Anybody using Lego? We do.
We want you to write a program using Scratch so when you put your finger in the crocodile's mouth, it will bite you.
In the same way that the crocodile fits together piece by piece, This computer code fits together like building blocks. All the commands you need on the left-hand side of the screen, which you drag into the middle to write your program. For this program, we're going to need to use the sensing commands, which tell the crocodile when to shut its mouth. The sensor value tells you how far you are from the crocodile's mouth. As your hand gets closer to the sensor, the number decreases. So you need to check what number it goes down to when your finger is in its mouth. Now that the croc is programmed to know when to bite, we need to program it so it knows how to bite. So we need to write some code for the croc's motor so its mouth will open and shut.
Great, so you've programmed yours to start biting your finger, right?
Yeah.
Okay. Do you want to show me what you did?
Okay. So as you can see, it's less than 20. And it won't bite unless it's under 20. And
So 20, that's the distance your
Yeah.
finger is from the sensor.
yeah, so when it closes, it stays on for 1 second, and then this way means it goes open. So it goes that way for 1 second, and then this way.
Oh, so it bites your finger for
Yeah.
1 second, then it lets go?
Yeah.
Okay, and that's all down to your programming?
Yeah.
Oh, that's so cool.
And it really is that straightforward to write a simple computer program.
Okay, yeah, of course it is. Right, okay. And the making things, of course, is part and parcel of how I think most of us are doing computing education. Again, reference to switched on computing. They make their own games in year 5. And one example posted onto the Twitter thing about what one class had made using Scratch there. And that sense of, look, here it is, here's what I made, have a look at it, folks. Coming back to David Brown's slides, notice the Ofsted logo obscured because of the terms of the Open Government Licence. This is inadequate achievement. So what is the worst way to do this sort of thing? He says it's when pupils rarely demonstrate creativity or originality in their use of computing that seem confined to following instructions. I suspect many of us will have seen, here is some instructions for you on the left-hand side of the screen, write your program on the right-hand side of the screen. That isn't learning to program. It's closer to programming children, follow instructions. Of course, we want children to follow instructions. But the creativity, the originality has to be there, to my mind and to his mind. Oh, one word of warning. If ever Ofsted say, can we take some photographs in your school? Just say no. There's no guarantee on which slides your photos will appear. Okay, it's not meant to link like that. And of course, this is what the children who get into Scratch are doing all of the time outside of the classroom. Again, remember the sort of building block metaphor here. So lots and lots of children making things to show to others, to share with others. For me, the clever thing about Scratch is not the building block stuff, but the share button up at the top of the screen there, that you can take your project and distribute that, show it to a global audience. This is one of the ones where there are people who I talk to who don't necessarily always agree with me about this, but for me, programming with a friend, programming with a partner, is a particularly powerful development strategy. Out in the real world, this is how software gets developed. A photo of one of Google's offices. This is a team of people working together to make things with software. Looks much more like a kindergarten than most of our computing classrooms do, but that's another story. And of course, teacher training here, we reference Vygotsky here, that the ideas that we have come not just through play, not just through making things, but through talking to other people, particularly our more knowledgeable others, zones of proximal development and that. Listening to somebody who can program, explain how it works. Very, very powerful. That doesn't need to be you. That can be their learning partner. And again, out in the real world, this pair programming methodology of two programmers working on one screen, one keyboard, one mouse between them, seems to produce better code more efficiently than the two of them working separately and then trying to put their work back together. Two brains really do seem to be better than one. I know what we're trying to do here is not produce working software, but produce working knowledge that children learn about computing. But I think the fact that this method of programming works so well out in industry should be some consolation for us wanting to do the same sort of thing in school. And again, the teamwork effort, the Scratch discussion forums about posting into the discussion forums about the problems you're having, real programmers posting into Stack Overflow about the difficulties that they have in getting the community to respond. This is part and parcel about how we learn this stuff. Don't feel the conversation has to be restricted to just the children in your classroom. Encourage them, perhaps, to take part in that wider community, subject, of course, to your school's e-safety policies. And we have great tools for collaboration there. Anybody using Google Drive? Google Apps for Education in your schools, your organisations? Brilliant for collaborative work, for working collaboratively on documents. The great project of Wikipedia, produced collaboratively by everybody contributing something of their own insights. Of course, we don't take it on trust, but the rest of the web is made up by people too, and we should be critical and sceptical about some of this. We're talking of Wikipedia. Anybody using simple Wikipedia? So Wikipedia are really complicated articles, not something I'd want to use with primary school pupils. Simple.wikipedia.org, simple English versions of those, much more appropriate for primary education. And again, when it comes to software development, projects like GitHub doing that collaboratively. We do this with trainees at Roehampton, so they have to produce an educational game as part of their assessed work, and we make them do it with a partner. Because firstly, we believe that it's quite important that teachers are able to collaborate with other teachers and learn to trust one another and learn that they can't let one another down when it comes to this sort of thing. And secondly, because working with a partner is a really good way of learning to program. Okay. I'm doing the thing about not having enough time to finish this properly. Okay. The other one, or one of the other points I'd want to make is about how important debugging is. We wrote it explicitly into the national curriculum about children should correct the errors in their code. The story, I think, is an interesting one. Way, way back when computers were real computers, made with electromechanical relays. You've got to imagine two blades of metal here, right? So a circuit could be completed if the blades touched. An electromagnet underneath. Put a current through the electromagnet, closes the circuit, current flows elsewhere. So you have one circuit controlling another circuit, which is still how computers work, although not with electromechanical relays. So the story was, back in the 1950s, the computer wasn't working. They couldn't figure out what was wrong with it until they noticed that a moth had flown in between the blades of the relay. So the electromagnet couldn't close it, so that bit of the switch didn't complete. The Americans, of course, called the moth a bug, and so removing the bug allowed the computer to work, and hence debugging. It's semi-apocryphal, but Grace Hopper's notebook, relay number 70, panel F, moth in relay. First actual case of bug being found. Stuck into the notebook. There's our bug report. I think that's exactly what Ewan was talking about. The physical bug stuck into the notebook, which was quite nice there. Anybody aware of Carol Dweck's work, Growth Mindset? Should do again the negative. Anybody not aware now of this? And she talks about how important your attitude to mistakes is. As Ewan had, first attempt in learning is the fail. It's the attitude when it goes wrong, when you can't do it, that seems to make a difference, of wanting to get better, of seeing that as something which is an essential part of the process. And your pupils who have that positive mindset, growth mindset, when it comes to things that go wrong, are likely to succeed much better when it comes to programming. And indeed, in programming, it goes wrong all of the time. So what you can't do is sort of run in circles, scream and shout. You have to develop this sort of growth mindset. Actually, my friend Quentin Cutts, who's Professor of Computer Science Education or Computer Science up at Glasgow University, did the experiment. He took half of his undergraduates and taught them about mindsets and made the case to them very clearly about your attitude to your programming will matter. If you're willing to stick at it and work hard and not give up when it goes wrong, you will do better in this course. He taught them that and gave them strategies for what to do when it went wrong. And the other half he just taught computer science to as per normal. And surprise, surprise, the half that was taught the growth mindset stuff did better in the final exam. It made a difference for his runners. And I suspect it may for our learners too. And again, we come back to Seymour Pappett's work, 1980, not 1993, that in programming it goes wrong all of the time. Okay, learning to be a master programmer is learning to become highly skilled at isolating and correcting bugs, the parts that keep the program from working. The question to ask is not whether it's right or wrong, but if we can fix it. And Papert argued back then that if we took that attitude of looking at where we can fix things when they go wrong and applied that to learning across the curriculum, then children would do so much better. They would be less intimidated by fears of being wrong. It's a persuasive argument. And we have illustrations of this in action. Here is more cracking the code material. Have a look at the racing car simulator.
In this program, we're using a variable to store the speed of our car. We can change how fast the car moves by changing the value of our variable.
What do we do now?
Well, we need to put speed in
Okay.
and set the speed to
A value.
10.
10, okay.
And then when I press the flag, it should go
Oh,
round.
oh yeah. Oh.
Whoops! Looks like this car's having trouble staying on the track.
How come it's going off?
Not sure.
Should we try slower speed so we've just got a bit more time to see it?
So let's try 5.
Yeah. Cool.
Okay, so what's going wrong there? Is that a bug, or is that actually closer to a feature? Here is an example that's the solution version. Let's have a look at the problem version. Debugging the racing car. Okay, so if we set the speed up initially as quite small, pop it on the track, let it run round, it trundles nicely around the track, okay? If it goes off to the left, it steers to the right. If it goes off to the right, it steers to the left. I assume Google's self-driving cars are no more sophisticated than that. But if we increase the speed to 10, then as you saw in the video there, horrible things happen. Etc. Yeah? Now you could say that's just a very good simulation. If you drive too quickly, you will lose control of your car. But you could say, how do I fix that so that it actually stays on the track even for high speed values? Any thoughts? Click on the link on the deck and see if you can fix it. It's not an easy one to solve. And yeah, we can come back to it. You can come and ask me
How
for...
do we get to your presentation?
Okay, all of the slides are at this address, bit.ly/PRACPED. That's PRACPED15, and then this has got a 1 at the end. How are we doing? Oh, Lord, there's so many bits to go through. Okay, and 7 minutes left. We'll see. Okay, very, very quickly for the last 3 then. Going for breadth, not depth. There are so many tools out there for the things that we can use to teach computing. So you have all of this list of programming tools that are available. I know that there are schools which say we've got to cover all of them. We've got to do coding, we've got to do Scratch Junior, we've got to do Scratch, we've got to do App Inventor as well. Let's do some Python as well. And to my mind, what you're doing there is just learning how to use the environment. It's far better to develop a... Oops, sorry, you wanted the slide back. Okay, there you go. Right, there are more than that. It's far better to think about the conceptual understanding here. That our aims for computing is to understand and apply fundamental principles and concepts of computer science and have repeated practical experience of writing computer programs. I think it's an element of the old style ICT is about learning to use software that we've applied to computing. We think it's learning to use particular programming environments. It shouldn't be. It's about mastering difficult ideas. We have this notion of the threshold concept, the thing which is hard to acquire, but once you've got it, your way of seeing the world changes. Abstraction would be on my list. Variables would be on my list. Here is my list. So looking at Key Stage 2 computing and highlighting in green the stuff which is hard to grasp. But once you get this stuff, then everything else moves on into a new realm. You start to see things. You start to see computing differently. And the variable question earlier, the A is 10, B is 20, A is B1. It's not easy. But once somebody explains it properly, better than I did today, then your understanding of that element of computer science changes permanently once you get it. So yes, we have all of those tools, but do you really need anything more than the list of, well, probably just the top 3 on the board? Bebop, Scratch, Junior, Scratch. What else do you need in order to teach the programming bits of the computing curriculum? Key Stage 1 and 2. I personally would move into Snap by the time they get to year 6, because I think 4 years of Scratch may be enough for most of them, and having somewhere to move on to. It's a similar set of tools. I wonder about Python. None of you are using Python. There are those who say we ought to be introducing that before they move on from primary school. They have plenty left to do in secondary school.
Code Combat.
Yeah.
We use Code Combat.
Okay.
For Python. It's really good. It's engaging and I use it, well, it's 5 to 6s. but if they use it, that's a good introduction.
Okay.
Website.
But my argument would be, and fine if it works for your learners, that's absolutely fine, please don't misunderstand me. To my mind, it's better to be really good at Scratch than really bad at 30 languages.
My kids don't like Scratch.
Because it looks so easy.
No, it's just they just don't get on with it. So
Yeah.
they find it just a bit too, I don't know, they don't like it. So yeah.
I'm sad to hear that.
It is
Yeah.
very easy to get, but I mean, you have to move with what the kids want, don't you? So I've tried them with it.
Fair enough. Okay, if it works for you. But in Scratch, you can do really quite complicated, subtle things from computer science. The code on the board plays the guess a number game. I'm thinking of a number between 0 and 127. Run the program through, and it will get to that answer. These are complex ideas. This one is Snap rather than Scratch and does fractions arithmetic. You're not going to run out of things to do in Scratch or Snap that need text-based programming. Getting a child by the end of primary school to write a binary search algorithm or to code up a binary search algorithm, which is what this is, or to code up fractions arithmetic, to teach a computer how to add fractions together. That's ambitious stuff. Okay, it's not going to be as exciting as making a game, but perhaps there's enough making games and we need to move into more conceptually demanding territory, which itself is quite exciting. Oh, and the coins problem. How many coins does it need? How many different ways can you make 15p? You can do that in a spreadsheet. Okay, other points very quickly. Nurturing their curiosity. They come to you with a model of how the internet works, of how computers work. Ask them those questions. Get them to draw pictures of the internet. Get them to ask questions. I've got a daughter who's just started primary school in reception. What I want her to do is to ask her teacher questions, not just to answer the ones she's asked. That's going to be really annoying, isn't it? Back in 1967, the Plowden Report, one of the main educational tasks of the primary school is to build on and strengthen children's intrinsic interest in learning and lead them to learn for themselves. They got that right back then. I think most of us still see that as what we should be doing. When Ewan said, what are your objectives? What's your objective? I wrote down 3. Nurturing curiosity, developing creativity, and strengthening character. But I'm not quite sure about the strategy bit. And then, of course, connecting to other people, making the links, being able to Google things, being able to find out the answer to a difficult problem, not by saying, Miss Sir, can you solve this for me, but by looking it up for yourself. John Hattie, who again Ewan referenced, looking through all of the meta-analyses of randomized controlled trial education research, says in one sentence, the biggest effect on student learning occurs when teachers become learners of their own teaching, when we get better at what we do, but when students become their own teachers, and provides hard evidence to support that. You can devolve some of the responsibility for learning how to program, learning about computing, to them, that they can teach themselves things. Think how powerful that will be moving forward. Again, our friends at Ofsted, that now a school will not be graded as outstanding in terms of teaching and learning unless pupils love the challenge of learning and are resilient to failure. Curious, interested learners seek out and use new information to develop and consolidate and deepen their knowledge, understanding and skills. And it's great that Ofsted see that as important. It really is. Finally, 1 minute. The key thing, the thing that's really radical about the English computing curriculum is not putting computer science into primary schools, but saying this is for everyone, that all children in primary education should learn some computer science, not just the geeky few, not just those who choose to do it later. Tim Berners-Lee tweeting at the Olympic opening ceremony. What are the consequences of that? Build on early success. They've got to have the firm foundation before they go forward. Teach them about problem solving before you teach them about programming. Teach them about being resilient to failure, about fixing problems when they go wrong, before you say, now here's some Python code, or here is some Scratch code. And sustaining that momentum forward. So give a good couple of years to get really good at bblots. Give a good 4 years to get really good at Scratch before moving on to Python, which some would otherwise really struggle with. The early foundations really do seem to matter. There are gender issues here. This was computer engineer Barbie. Your robot puppy is so sweet, says Skipper. Apparently Barbie's sister, who knew? Can I play your game? I'm only creating the design ideas, Barbie says. I'll need Stephen's and Brian's help to turn it into a real game. Is this a positive gender role model that we have here? She got so criticised for this. The binary code, if anybody's sufficiently geeky, spells Barbie. Okay. Emma Mulqueeny, Young Rewired States founder, says Year 8 is too late. One of the reasons why putting it onto the primary curriculum matters is because if girls get interested in this at primary school, they're likely to want to carry on with this when they get to secondary school, or at least that's our hope, or at least they'll have the choice to do so. That really is what we're looking for here, and the peer pressure thing will be less of an effect. So, is anybody in the room able to name all 5 people on the slide here? Okay, Ada Lovelace. I think it was Ada Lovelace Day on Tuesday or something. First computer programmer. Anybody? Mark Zuckerberg founded some sort of website somewhere. Found the first bug, allegedly. Sergey Brin. Does that help anybody? One of Google's 2 founders.
It's got to be Alan Turing.
Of course it has to be Alan Turing. What do they all have in common? Well, they're all brilliant computer scientists. They also all came from nice middle class homes. Yeah? Or in some cases, upper-class homes. Yeah? There's an issue there. That if these are the role models we give, doesn't that say this is a socially elitist thing? Anybody know who this is? This is Tommy Flowers. Does that help anybody? Okay. Tommy Flowers built the first computer. We all know about Turing and Bletchley Park and all of that. But Turing had the theoretical idea of a computer and helped with the Enigma cracking thing, admittedly. But the first computer was Colossus, which was designed for another, even harder cipher to crack. And it was Tommy Flowers' work. Tommy Flowers was a working class lad. He taught himself electrical engineering through night school. Night school, is that what we used to call it? It wasn't night school. He was a post office engineer. The work wasn't properly funded. He had to buy the valves himself for some, or the relays and valves for some of Colossus himself. And who played Tommy Flowers in the Imitation Game? In fact, nobody did, because he wasn't even a character in the Imitation Game. Yeah, it's not to deny the importance of Turing's work, of course it isn't. But there are other people who we ought to acknowledge as heroes there too. And this should be a socially inclusive thing. If you don't do it on the curriculum, then what you end up with is it's only those who have nice middle-class families whose parents think this is something important. Whereas computing is a meritocratic field. It's not where you went to school. It's not who your parents are. It shows your code. Can you write something that works? Okay, this was how I learned to program. I'm not going to go into the details now. In terms of special educational needs, there's an obligation in the English curriculum to set challenging tasks for those who have special educational needs as well as others. The old P levels were never revised alongside the rest of the ICT to computing curriculum, but much of this is directly relevant to the stuff about computational thinking. Perform actions often by trial improvement. That's the beginning of an experimental, logical reasoning approach. They know certain actions produce predictable results. My logical reasoning thing is in there. The computational thinking, if not necessarily the Python programming, is there for all. And you have inclusive and assistive technology such as Makey, which is fab. Don't know why. Oh yes, and then there was English as an additional language, where you get with Scratch the ability to swap the language pack out, which is my version of Scratch was showing French this morning. So if you have a child who can't communicate in English but is fluent in another language, they can still do Scratch programming by simply swapping the language pack over. I have programmed in Korean in front of an audience of native Korean speakers without any Korean myself, because I can recognise what a Scratch block looks like when I come to it. I have overran, but only ever so slightly, which is good by my standards. As I told you, former primary school head teacher in assemblies, nobody could tell me to stop talking. You know how it is, folks, don't you? I was going to put that list back up, but before I do that, does anybody want to ask any questions, make any comments, say, Marge, you were just so wrong about this, that, or the other? Okay. Let me quickly go back to the second slide in the deck, because there is that question. I don't want to just leave entirely hanging there. It's my top 10. I claim no authority for this. Do you think there's things there which don't matter, which aren't necessary? In your experience, would you add an 11th or a 12th in? Is there something I've missed out? Is it that we're all in broad agreement around this, or is it just that we want a coffee now, please?
Yeah, I like it.
Okay. Well, thank you ever so much.
Thank you.
Joining in.